Hello everyone, this is Qusay Al-Umari and I'm going to do the data commentary on a special topic in my field, which is the relation between stress and strain for steel alloys. At first, I'm so sorry because I don't have any audiences and I couldn't go to the university and use the data show projectors. So I'm going to use this program that records me and the screen simultaneously. Okay. So figure 1 here, or this figure in general, shows the relationship between stress and strain for a steel metal which being tested under axial tension. So as it can be seen here, the x-axis represents the strain, which means the deformation of that steel alloy, and the y-axis represents the stress, which is the force per unit area. And also we can see here that the area under this curve can be divided into four regions. The first region is elastic region, then yielding region, after that strain hardening, and the final one is the necking. And also the curve can be divided into two main zones. The first zone is the elastic zone, at which the material will behave elastically, and the second one, which combines both of these three, one yielding, strain hardening, and necking, called the plastic behavior. First of all, if we take a look here for the elastic region, we can see that the relation is the relation of stress and strain is a linear one, and that means that the steel alloy can be returned to its original case without any further deformation or permanent deformations at this zone. So if we load the specimen up to one of these 2 points, the steel specimen can and we after that remove that load, the steel specimen can return back to its original state. So we can see here that the elastic region starts from zero stress or zero force and reaches up to what we call sigma y. This sigma y called yielding stress. The yielding stress here is the end of the elastic region and the end of the elastic behavior of that steel. After that, and after this sigma y, the specimen will exhibit more deformations, and these deformations are not recoverable. So the deformations are called plastic deformation. The first region here, which is the yielding region, we can see that with approximately constant stress, the steel specimen exhibits a very large deformation or plastic deformation. And after that, and at the end of that yield region, the specimens start to carry more load, and we can see here the curve is going up, so the stress increases, and also the specimen is still exhibiting a plastic deformation. And when the specimen reaches to this point, which called sigma u or ultimate stress, the ultimate stress or ultimate strength is the capacity of material to carry load before rupture or before cracking. And after this point, the specimen will be necking, or the cross-sectional area of that specimen will be reduced, and therefore it will be fractured at the end of that region, which is necking. So we have also the stress at fracture or at cracking of the specimen called sigma f, which is the failure or fracture stress. Okay, so in general, To conclude, this stress-strain diagram is specified only for mild steel. Mild steel, which is a composite material of steel, or sorry, iron with carbon with low percentage or low proportion of carbon. And this stress-strain diagram cannot be generalized for all materials. For example, if we take the stress-strain diagram for glass, it will also start by elastic region. But the difference here, the glass is a brittle material, or a very brittle material that tends to crash. It starts by the elastic region, but the plastic region will be very small, so it will go up to here and will go from the yielding to the fracture with very small area, or with very small time, or very small plastic behavior or deformation, and it will crash. So to sum up, this stress strain curve or diagram is allocated or drawn just for mild steel, and it can be done for many other materials. Thank you for your listening, and see you again soon. Bye bye.